Let's go ahead and do SO2. It's going to be a little bit more challenging, so pause the video as you see fit. We need to go ahead and split this apart into sulfur and oxygen and do our math that we did before. Let's go ahead and work through the math quickly. We have 1 sulfur and 2 oxygen. They're both in group 16, so they both have 6 valence electrons. Go ahead and multiply across, and we have 6 and 12 that we need to add together, thus giving us 18 total valence electrons for this molecule. We now need to orient the atoms. Remember, we have to look at the electronegativity values. Here's our chart once again, and we can see that sulfur is 2.5 and oxygen is 3.5. So let's get that down on our paper and move on. As you can see on my piece of paper, I wrote down my electronegativity values, just to be safe. The least electronegative goes in the middle, hence why sulfur is between the 2 oxygens. It really doesn't matter how you orient the oxygens around the sulfur, as long as they're as far apart as possible. Step 3, place a single bond between each atom to connect them. This is the point where we also start our simple math calculations. We have to remember how many total valence electrons we had from step 1, which is 18. So let's go ahead and get that math started. On the right hand side, I have 18 valence electrons. That comes from step 1. And I'm subtracting 4 valence electrons because each one of the bonds that we just made, here and here, are made up of 2 electrons each. And now we have 14 electrons left over. At this point, proceeding to the next step, we'll actually be able to place those 14 electrons onto our atoms. Continuing on with step 4, place electrons on the outermost atoms one at a time until octet is reached or until you run out of electrons. Now normally when it says one at a time, it means you're going to do one atom first before moving on to the other. However, when adding your electrons, you should be adding them in pairs. So going ahead and starting to place your electrons, it doesn't matter which oxygen you start placing them on, as they are the outermost atoms. The S is the central one, so please don't add anything to that in this step. Here you can see I added 6 electrons to the oxygen, and there's a reason for this. You want oxygen to reach octet before you start moving on to the other oxygen. Because we had 14 electrons left over from our last step, we're able to put 6 more into this oxygen. And let's see if we have octet. We have 2, 4, 6 electrons in our lone pairs. And then we have 2 more electrons that are made up in our bond, thus adding up to 8. Now we can go on to the right-hand oxygen and place 6 more. Thus, we would be using 12 electrons in this step. So I will go ahead and write that math down and add our electrons. Again, this oxygen just mirrors the other one, but just for some more clarification, we have 2 electrons in the bond, 4, 6, 8. Thus, we have reached octet at this point. 14 minus 12, we have 2 electrons left over for step number 5. Starting where we left off, we have 2 electrons left, and step 5 says, if we have any electrons left, place them on the center atom, which would be our sulfur. Subtract our 2 from our total. And our goal by step 5 is to have 0 valence electrons left. Going on to step 6, now we have to use our formal charge and the octet rule to form double and or triple bonds if needed. Looking at our oxygens, we know from the previous step that both oxygens have octet, but does sulfur. So let's go ahead and count. Sulfur has 2 being shared in this bond, 4, and then 6 total being shared with sulfur. We are not at octet yet. So this is an indication that we need to make some double bonds. But before we do so, let's go ahead and do the formal charge of the sulfur and the oxygen at this step. Again, assuming that the oxygens are just mirror images of each other, we only have to do this calculation once. Alright, so here's our math for formal charge for both the sulfur and the oxygens. Each one of them has 6 valence electrons as we discussed in step 1. However, working through the sulfur has 2 bonds to it, and it also has 2 electrons, and so left over we have a 2+ charge. For oxygen, it has 6 valence electrons, minus 1 bond, minus 6 dots for each electron, equals a -1 charge, or just write down negative, since we don't have to write the 1. What I do need to note here is that you do 1 oxygen at a time, and because they're both the same, you just have to do it once. This indicates that we can have some movement of electrons, because at this point, we have a negative charge for each oxygen and a 2+ charge for the sulfur. Overall, if we add that all up together, so 2+, and then we add in 2 negative charges, we still have a 0 charge overall, but we want to minimize this charge and get sulfur octet. Now the shift of electrons that I'm about to do, you can either do it from the left or the right side. But I'm going to go ahead and take these 2 electrons here, and I'm going to bring them in and make another bond. So with blue, I'm going to rewrite the structure. Notice now on the screen, I moved those 2 electrons in to form a double bond. I went ahead and kept the notation of this negative because nothing changed here. So I don't have to recalculate formal charge for this since nothing changed. However, for the sulfur or for the oxygen on the right, there was some movement, so we have to recalculate those 2. So let's go ahead and do formal charge for both of those. Now on your screen you can see formal charge of sulfur. Again, it wants 6 valence electrons, and now has 3 bonds to it, and it still has 2 electrons as a pair, and so doing that math, that now has a +1 charge. The formal charge of the oxygen that's on the right hand side still wants 6 valence electrons, but it now has 2 bonds and 4 electrons. So overall, the charge of the oxygen on the right is 0. If we look at the structure now that's in blue, we minimize formal charge because now instead of having a negative, a 2+, and a minus, we now clearly have a -1 charge, a +1 charge, and a 0 charge. So comparing the green structure to the blue structure, you should be able to see that the formal charge has decreased, even though if we add up mathematically, they both still have a 0 charge. The last thing that we're really aiming for is for the sulfur to have octet. Remember, we're following octet for this structure. So if we take a look at this, our bonds each have 2 electrons each, so we have 2, 4, 6, and then 8 from this top one. So that's an octet. And just to clarify and go over the oxygens one more time, this oxygen on the left has 2, 4, 6, 8, so octet is reached on the left, and 2, 4, 6, 8 for the oxygen on the right. We now have our Lewis structure for SO2. There's one last piece that we need to include. I've been mentioning you can take the electrons from either the right or the left side. You can start with the right or the left side when you start going through these things. But now that we went ahead and have the double bond on the right, it's also correct to do this for the left-hand side. So to represent this structure completely, we have to do what's called a resonance structure and show both options. All right, so here we go. This is showing both resonance structures. And by normal notation, you would go ahead and put them inside brackets. Obviously, if you have more than one, you would want to extend your brackets, and you put a double-headed arrow between the 2. You can do resonance showing where all the bonds would be. For instance, if you have a double or a triple bond, you'll want to show every single location that they can be in. And the other way that resonance can work is if you have more than one exterior atom or outermost atom, like for instance, if one of those oxygens was a different element, you would also want to show all the possibilities and different arrangements that those 2 atoms could be. So move them around to show every single orientation that they could be in. I hope now that you have a solid understanding of how to do a Lewis structure. If you follow these 6 steps, I'm confident that you will be able to approach any molecule that you might be given.